Okay, we can start. Welcome to the third meeting of the European Non-Associative Algebra seminar. I'm glad to introduce the speaker of today, Professor Karel Dekimpe from the Catholic University of Leuven in Belgium. The title of his talk is Di-semisimple Lie algebras and applications in post-Lie algebra structures. Please.
Okay, thank you very much for this introduction, and also thank you very much for inviting me to give a seminar at this online seminar. I think it's a great event that you are organizing, so thank you for doing this. So everything I'm going to talk about today is joint work with Dietrich, Burde and Mina, Monadjem. Both are present today, so they can correct me if I'm lying. And so first of all, well, I have to excuse myself because my voice is not as it should be. And I hope that I will survive my own talk because I have a great cold. But please do not blame me. Oh, the fault is this guy who D something Lie algebras. Well, okay, recording again. So let G be Lie algebra written as a vector space sum of two subalgebras. So it's not a sum of ideals or whatsoever. You just have two subalgebras, A and B. Yeah, you have a vector space sum, either direct or not. And then the question is, can we say something about the structure of G if we know something about the structure of the subalgebras? Yeah, and probably when we have a direct sum over here, we can say more. And so if the sum is direct, we will write it as a plus with a dot above. So this is a direct sum of vector spaces. Yeah, if I use this, let's say, normal way for denoting direct sum, I mean a direct sum of Lie algebras. So if I use this notation, then elements from A and B commute. So the bracket of an A and a B is 0. Here, it does not have to be 0. So they are just subalgebras, not ideals. So just to say what the notation means. Okay, and maybe let's start at the very beginning. What if A and B are both abelian? Well, an easy example is you take the two-dimensional solvable Lie algebra. So you have two basis vectors. Yeah, and the commutator or the bracket of two of them is one of the two. Yeah, then of course you can take as subalgebras two one-dimensional spaces. E1 generates A and E2 generates B, and of course these are abelian, and you can write the Lie algebra G as the direct sum of these two subalgebras. And of course it's solvable. Yeah, so you see, if you start with the abelian ones, you can get solvable Lie algebras. Solvable here of derived length 2, so metabelian. And actually this is all you can get. Yeah, so already in 65, Coleman proved this little result that if you have the sum of two, if G is the sum of two abelian subalgebras, it has to be solvable of derived length 2. So it has to be metabelian. And this is just a very short proof, nothing difficult. So there is also no restriction on the field. It can be any characteristic. It works for infinite dimensional Lie algebras. So this is quite an easy result. Probably many other people have proven the same thing in other papers. I don't know. Okay, then the next part, the next result is, what can we say if you replace abelian by nilpotent? Yeah. And then the result, yeah, well, actually it's 3 years before, in 62 says, well, if you look only at finite dimensional Lie algebras over fields of characteristic 0, then it's true that if G is the sum of two nilpotent subalgebras, it has to be solvable. And actually also vice versa, if G is solvable, then you can find two subalgebras which are nilpotent and which together generate Lie algebra G. No question? No. Okay. Some remarks about this result is that despite what we had the previous thing. So in this result, we had nilpotency class 1, nilpotency class 1, you get derived length 2. Yeah, here we cannot say anything. Well, not yet. So if you have nilpotency class something, nilpotency class something, we do not really know anything about the derived length of G in general. Yeah. One of the questions is this derived length bound by a linear function in the nilpotency class of A and B? Moreover, here being of characteristic 0 is important because the result is certainly not true in characteristic 2. Yeah, so Petrovchuk proved this. I don't remember exactly the date. Yeah, but it is true for other characteristics. Yeah, so I think Panyukov proved it in general and Zuzmanovic for characteristic above 5, something like this. Okay, and in the infinite dimensional case, many things are open. Yeah, there are some partial results. For example, when one of the two is finite dimensional and the other one is infinite dimensional, then the result is also true. But in general, we do not know. Okay, what about sums of solvable subalgebras? Well, look at, let's say, GLN or SLN. Then, of course, you can write such a Lie algebra as a nilpotent one and a solvable one, even a direct sum of vector spaces. And so you can get here simple, reductive, semi-simple, using nilpotent and solvable. So actually, can we say anything is, let's say, game over? Yeah. Does everything stop at the nilpotent case? Well, actually, it doesn't. And we have been working on further cases, namely, what about sums of semi-simple Lie algebras? If you look at this, then of course, G will not be solvable anymore, but can we say something? Okay, and then to keep notation a bit short, we will say that the Lie algebra G is Di-semisimple if it can be written as a sum of two algebras, and strongly if you have a direct sum. Yeah, so this is just the notation that we are using over here. Okay, and then we only started to study these kind of things, and a very simple result says that for these semi-simple Lie algebras, they all have to be perfect. And of course, the proof is quite simple. Yeah, if you write G as the sum of two semi-simple ones, then you take the bracket of G with itself. You just work out, and you already get S1 with S1, S2 with S2, which generate S1 and S2. So you get everything over here. So certainly, these semi-simple Lie algebras are always perfect. Okay, can we say more? Well, I will talk about strongly these semi-simple Lie algebras in a moment, and I will prove some lemmas and results. And in these lemmas and results, I'm going to use some basic facts. And of course, the first fact is very well known. If you have any finite dimensional Lie algebra for field of characteristic 0, then you can write it as its radical. And together with the semi-simple Lie algebra, which is called the Levy subalgebra. So any Lie algebra can be decomposed in this way. And actually, any semi-simple subalgebra of G is contained in a maximal one, which is a Levy subalgebra. And two Levy subalgebras are actually isomorphic to each other, conjugate by an automorphism of the form e to the power the adjoint of Z, where Z belongs to the radical. Yeah. So this is a result that I will be using over and over again in what follows. And then maybe something which is not as well known, and actually we proved it about 10 years ago when we were studying some other stuff. It says the following: if you have a semi-simple Lie algebra, then you have a module over S. Yeah, so you have a representation from S to GLN to GLM. Yeah, and if the dimension of M is at most the dimension of S, then you have the following result: take any element of your module, then its annihilator will be non-zero. So there will always exist a non-zero vector in the semi-simple Lie algebra such that X times M gives you 0. Yeah. And for this, it's very important that you have this restriction on the dimensions. So the dimension of the module has to be at most the dimension of S. Actually, if it's strictly less than S, it's trivial. So you only have to give a proof when the dimensions are equal. Yeah, and that's what we did in 2013. Okay, and now what did we do? Well, we proved some results in order to be able to say something about strongly Di-semisimple Lie algebras. This will be the main result of today. So the first lemma says the following. So if G is such a strongly Di-semisimple Lie algebra, so you can write it as a sum of direct sum, vector space sum of two semisimple subalgebras. Yeah. Then neither of these semisimple subalgebras can be a Leuven subalgebra of G. Yeah. Okay, so let's prove this. So assume that one of the two is a Leuven subalgebra. So this means, for example, S1, they play the same role. So in that case, you would be able to write G as the summative product of its radical and the S1. And of course, then the dimension of the radical has to be the dimension of S2, because yeah, the dimension of S2 plus S1 is the dimension of G, and the same holds for these dimensions. So we have that the radical is then of the same dimension as S2. Yeah. Okay. Now we use the result of Leuven and Monadjem saying that, well, this S2 is a semisimple subalgebra of G, so you can find some element in the radical, yeah, such that if you apply the automorphism e to the power add z to the S2, you have to arrive inside the Leuven subalgebra. Yeah? So such a z exists. Yeah? Okay, the radical, of course, is an ideal of G, so it's a module over any subalgebra of G, so it's certainly an S2 module if you just use as the action the Lie bracket. And as I said, the dimension of S2 is the same as the dimension of the radical. So we are exactly in the situation of this lemma. We have a module M, the radical, which is an S2 module, and they are of the same dimension. Then by this lemma, we know that for any element in the module, there is some element in S2 such that you get that this is 0. Yeah. So I apply this here, yeah, for the element Z. Yeah, so Z belongs to the radical. So there is a non-zero x in my S2 such that x times Z, which is just a bracket, is 0. Now, if we look at what happens now for the image of x under this automorphism, you just write out what it means. So it's x plus then the series for the exponential map. Yeah, and of course, add z applied to x is 0 by this thing. And then if you do the square also, so it's just x plus 0, so it's just x. So x is a fixed point for this automorphism. Yeah. But we know that this automorphism sends S2 into S1. So this means that this x also belongs to S1, but the x already belonged to S2. So we started, yeah, with an element in S2. So this means that this x belongs to the intersection. It's a non-zero vector, so this is a contradiction because we have a direct sum decomposition. Yeah. So we have proven this lemma that none of these two subalgebras can be a Leuven subalgebra of G. Okay, so you see the kind of mathematics that we are using in our approach, and actually we are doing somehow the same of things to prove the second lemma. This is a little bit more complicated to formulate. So again, we look at a strongly Di-semisimple Lie algebra G, so written as a direct sum of two semisimple subalgebras. And let's say we pick a Leuven subalgebra which contains S1. Yeah. Then the claim is you can find a third semisimple subalgebra, yeah, which is isomorphic to S2 in such a way that this S can be written as S1 plus S3. And moreover, very important, we know something about the dimension of the intersection of S1 and S3, namely it's exactly the dimension of the radical. So this is some strange result perhaps, but this is what we prove. Okay, again, we start in the same way. So since S2 is a semisimple subalgebra of G and S is a Leuven subalgebra, we can find some Z in the radical such that if we apply the automorphism e to the power add z, we have that this phi of S2 ends up in S. And it's this phi of S2 that we will call S3. Yeah? So certainly S2 and S3 are isomorphic as Lie algebras because phi is an automorphism. Yeah? So we do have an S3 sitting inside S. And so I still have to prove that first of all, the S is now the sum of the two, and then secondly, that these dimensions coincide. Okay, this line is something which we will be using more than once. So if you have any element of your Lie algebra, and you have an automorphism of this form, so e to the power add z, where z is in the radical, yeah, then we will always have that y minus phi of y belongs to the radical. And why? Well, if you look at y minus phi of y, so this is this exponential, so this is just the power series, so the first term is y, and then you have k equals 1 to infinity of the other terms. And of course, z is the radical is an ideal of your Lie algebra. So applying add z to y gives you something in the radical, and doing this more than once stays in the radical. So this part always belongs to the radical. This is just 0. So doing y minus phi of y gives you an element of the radical. Yeah. And then we can start proving what we want. So take any element in your Lie algebra G. Remember, we are working with a strongly Di-semisimple Lie algebra, so it's can be written as a part over here and a part over here. So x is of the form S1 plus S2, where the small s1 belongs to the semi-simple Lie algebra S1, and the same for analogously for S2. Then we use the line above. So we play a little bit. We subtract phi of S2 and we add phi of S2 over here. Okay, phi, remember, phi was the automorphism sending S2 to S3 sitting inside S. So this phi of S2 is an element of S3. Yeah, and this element S2 minus phi of S2, yeah, this is of this form, belongs to the radical. Yeah? So you see that any element of G belongs to the sum of S1 and S3 plus something in the radical. And of course, this part we know is sitting inside the Leuven subalgebra. Now, we know, of course, also that G is, as the Lie algebra, the direct sum of S, well, as a vector space, the direct sum of S and the radical. Yeah, so it's also the sum of, let's say, a subalgebra plus the radical. Then, of course, S has to be equal to this subalgebra. Yeah. So we did prove already the first part, that S equals the sum of these two. Okay, and now some easy dimension counting. So the dimension of this S is just the dimension of the two subspaces minus the dimension of the intersection. And of course, on the other hand, we know that G is the direct sum of S and the radical. Yeah, so the dimension of S is the dimension of G minus the dimension of the radical. G is also the direct sum of S1 and S2. So the dimension of G is the same as the dimension of S1 and the dimension of S2. So we get actually that dimension of S can be expressed both in this way and in this way. Of course, these are the same. The red ones are also the same because they are isomorphic. And so as a conclusion, we have that the dimension of the intersection is really the same as the dimension of the radical. Okay, so this was the second lemma. The third and the fourth lemma I will not prove. So lemma C and D are as follows. So the third lemma says that if you know already that S is semi-simple, and you can write it as a sum of two semi-simple subalgebras, so it's Di-semisimple. So you have this form. Then we can prove that the intersection of S1 and S2 has to be zero or semi-simple. And the proof of this result is actually heavily based on arguments from two papers of Onyshik. So he has been studying decompositions of reductive Lie groups and the algebras in two papers, and I give the two papers over here. Somehow this result is not formulated as such in his work, but I guess he must have known this result. We were able to actually prove this result by using, well, parts of proofs of results that he did. So I think we had to collect three theorems and then parts of proof of these theorems and then add something more before we could prove this. So it's a lot of things are going on before we can prove this. And here it's actually very crucial also that we are working over C. Okay, so we have this nice result that if you have a semi-simple subalgebra that you write as a sum of two subalgebras, which are also semi-simple, then the intersection of the two also has to be semi-simple or zero. And then another result that we will be using is the following lemma. So this is due to Kosul. He says that if you already know that S is semi-simple, yeah, and you can write it this S as a direct sum of two subalgebras, then actually you can find an ideal in S which is isomorphic to S1 and an ideal which is isomorphic to S2, such that S is really the sum of this direct sum of these two ideals. So S will be isomorphic to the direct sum of S1 and S2. Of course, these guys do not have to be ideals, but you can find ideals which are isomorphic to S1 and an ideal which is isomorphic to S2 for which S decomposes as a direct sum. So, but the main part is that he has to assume already that this S is semi-simple. Our main result says the following. So this is what we proved last year. So together with Dietrich and Mina. So if you know that G is a strongly Di-semisimple Lie algebra, so you can write it as a sum of two semi-simple subalgebras, then actually G is also isomorphic to S1 and S2. Yeah? So the main difference is that we do not have to assume now anything on G. It follows that G will be semi-simple. Actually, this is what we have to show, that G is semi-simple. Yeah? And then we get really that this G is isomorphic to the direct sum of these two by applying the result of Kosul. Okay, let me try to go through the proof of this result. So, well, we have to show that it's semi-simple, and then the rest follows by Kosul. So we assume that it's not semi-simple. So this means that the Lie algebra has some non-zero radical. So the radical is of dimension at least 1. Yeah. And then let me go back to lemma B. So recall, lemma B said, yeah, if you have such a strongly Di-semisimple Lie algebra, then you can write the Leuven subalgebra, which contains by assumption S1 as a sum of S1 plus S3, where this S3 is somehow a phi of S2, and we have this result on the dimensions of the radicals. So this is what we apply now. So we write S as S1 plus S3. So S1 we assume is contained in S. We can always do this. And so this S3 is somehow a phi of S2 where phi is of this form. Yeah. And we know that the dimension of the intersection of these two is the same as the dimension of the radical. So, and we assume now that this is at least 1. Yeah. Okay. And then what we have over here is that S is a semi-simple Lie algebra. It's a sum of two semi-simple subalgebras. And then the lemma that I could not give you a proof says if you have such a situation where you have a semi-simple Lie algebra written as a sum of two other ones, then the subalgebra is either 0 or semi-simple. So here I have that my S is the sum of these two. Yeah, and so the intersection of these two has to be either 0 or semi-simple, but it cannot be 0 because it has a dimension at least 1, so it is really semi-simple. Okay, so we know that this guy is a semi-simple Lie algebra. What we do now is, well, we take the inverse of this phi, so we call this psi for notation. Of course, this is just e to the power at minus c, so it's also one of these morphisms of this form. And so the S2 we can write as psi of S3. And now I have the claim that I will prove in a moment. And so believe me for a moment. The claim says that if you look at this Lie algebra, so you take S1 intersect S3. So this is a subalgebra of S, semi-direct radical. So this is in total a subalgebra of G. That you can write this as a direct sum of two semi-simple subalgebras, namely S1 intersect S3, which is semi-simple, and psi of this intersection. So this is, of course, an automorphism, so this is also semi-simple. Yeah. So we have here a Lie algebra that can be written as a sum, or direct sum of two semi-simple Lie algebras. Now let me go back to lemma 1. So we have that G, the S, is the direct sum of S1 plus S3. No, it's a, well, we have a Lie algebra which is the direct sum of two semi-simple Lie algebras. Then neither of the two can be a Levy subalgebra. And now let me go back to my proof. So here I have a Lie algebra, which is written as the sum of two semi-simple Lie algebras. So this means that neither of the two can be a Levy subalgebra. So certainly this one cannot be a Levy subalgebra of this Lie algebra. But actually it is, because this is the radical and this is a semi-simple Lie algebra, and we have this direct sum decomposition. So this is a contradiction. So the assumption that my dimension of my radical is at least 1 has to be wrong. So it has to be 0. So the Lie algebra G has to be semi-simple. Of course, we still have to prove this claim, which might seem a bit strange. So let me spend some time on proving this claim and try to recall what all the ingredients are. So recall the claim. So we have S1 intersect S3 similar to the radical should be the same as S1 intersect S3 direct sum psi of this thing. Okay, first of all, recall that the radical and this guy have the same dimension. So this is the same vector space as this. This radical has the same dimension as this. So this means if I can prove that these two vector spaces, let's say, are the same. So this vector space is the same as this vector space. Then by dimension reasons, it's enough to show that this vector space is the sum of these two. And then we immediately get that it's a direct sum, just because the dimensions match up. Okay, let me start at the left-hand side and prove that any vector in the left-hand side also belongs to the right-hand side. Of course, for vectors over here, it's clear that they are sitting, that they are sitting inside this space. So it's enough to prove that any element of the radical also belongs to the right-hand side. Okay, take a vector in the radical, an element of the radical. Recall, I am working in the situation that my Lie algebra G is the sum of two semi-simple Lie algebras, an S1 and an S2. So I can write my Y as an element from the semi-simple Lie algebra S1, so this small S1, and an element of S2. Okay, this S2, recall, S2 and S3 are connected to each other with phi and psi. So S2 was psi of S3. So this S2 is somehow a psi of some element of the Lie algebra S3. And then I play again the same game as I did before. So I add S3 and I subtract S3. This element over here, remember this psi was such an e to the power add z. And if you do this, you always end up in the radical. So this element belongs to the radical of G. And of course, S1 plus S3, that we already showed, was S. So this element belongs to S. Okay, now we have that Y is an element of the radical, and we have written it as a sum of something in the semi-simple part and something in the radical. So this means that this part has to be 0. So the S1 plus the S3 has to be 0. Okay, if the S1 plus the S3 is 0, then of course S3 has to be minus S1. And since this guy belongs to the Lie algebra S3 and this guy belongs to the Lie algebra S1, these elements, which are the same, have to belong to the intersection. And so if you look at what's standing over here, so the Y is 0 plus this thing. So the Y is minus S3 plus psi of S3. And the minus S3, well, this is an element of S1 intersect S3. So this is sitting inside here. And the psi of S3, the S3 is sitting in the intersection. So it's sitting inside here. And so we proved really that this space is included, well, that this space is included in this space. The other way around is easier. So if you have that, well, take let's say two elements, an element over here and an element over there. So I call y plus psi of z, where z is also belongs to this. Again, do the same game. This is y plus z and then minus z. The y plus z, both of them belong to the intersection. So the y plus z belongs to the intersection. And this again, for the same reason, belongs to the radical. So any element over here also belongs over there. And this proves the claim. And so this ends really the proof of our main result on strongly Di-semisimple Lie algebras. Namely, if you have a strongly Di-semisimple Lie algebra, then the Lie algebra itself is actually semi-simple. Yeah? And it's isomorphic to the direct sum of the two components of your direct sum. Okay, so we can indeed say something about strongly Di-semisimple Lie algebras. Can we say something more just for Di-semisimple Lie algebras when the sum is not correct? Well, actually, one cannot say too much. So we know that the Lie algebra has to be perfect. Yeah, but certainly it does not have to be semi-simple. Yeah? For example, if you just look at the Lie algebra SLNC semidirect Cn, so where this guy is acting just on the column vectors over here by multiplication. So you can view this Lie algebra G as consisting of all n plus 1 by n plus 1 matrices of this form. So this is the Cn part. And so you ask that the trace is 0. So it's just, oh, sorry, this has to be SLNC, and this is Cn. Yeah. So this is this part. And then you can easily show that actually this Lie algebra, you can write it as SLNC. So with zeros over here. And then you choose a nice vector over here, such that if you look at applying this automorphism to SLNZ, that you get anything you want in this column, all possible elements, and you can easily see that you can write such a Lie algebras as a sum of two semi-simple Lie algebras without G itself being semi-simple. So you see it's perfect, but not semi-simple. So we cannot say too much if we do not ask for strongly Di-semisimple Lie algebras. Okay, and this finishes the first part. So we have proven that strongly Di-semisimple Lie algebras have to be semi-simple themselves. Now let me move on to the second part. So I want to talk a little bit about post-Lie algebras. And so if you got lost during the first part, don't worry, you can restart and listen again. So we will only need to apply the main result once. So the rest you can forget now. So what are post-Lie algebras? Well, actually, I will define what is a post-Lie algebra structure. Yeah. So what we have is, as ingredients, we have given a vector space V, finite dimensional over the complex numbers, although you can define this in general, of course. And then we consider two different Lie brackets, maybe different. It can also be the same. So we have, let's say, square brackets and curly brackets, such that both brackets are really Lie brackets. So the square brackets, I denote the vector space with the square brackets always by a G, and the vector space with curly brackets always by an N. And then a post-Lie algebra structure, shortly PA in the sequel, on this pair of Lie algebras. So a pair of Lie algebras is actually two Lie algebras on the same vector space. So a post-Lie algebra structure on this is a bilinear product on the vector space, such that these three conditions hold. Okay? So the first one says that the bilinear product has some connections with both brackets, and then something else that I will comment on in a moment. Well, maybe I should comment on this directly. Yeah. So if you look at the above, yeah, what we can do is we can use L of x to denote left multiplication by x. Yeah? So L of x applied to y is just x times y. Yeah. And so this third condition, if you read this shows that L of x applied to this bracket is L of x applied to y plus y L of x applied to z. So this just means that L of x is a derivation of the Lie algebra N. Recall n is with curly brackets. And then the second condition just says that if you look at the map from L from G to, well, we already know we are ending up in the derivations, that this is really a Lie algebra representation. So the L of the Lie bracket is the Lie bracket of the L's. So this is a better way to remember 2 and 3. Yeah. So actually, if you say that this is a representation, then the fact that you end up in there n shows that every L of x is a derivation of n, and that it's a representation means that the second condition is satisfied. Yeah. And then the first just says that the difference of the two brackets is, well, what is often what you hope for a bilinear product to define a Lie bracket. Okay, so these post-Lie algebra structures were introduced, I forgot the year, by Bruno Valette when he was studying posets. I have actually encountered these post-Lie algebra structures from a geometrical point of view when studying geometric structures on Lie groups. These are always also connected to Rota-Baxter equations. They pop up in physics. So there's a lot of people studying these kind of things. And I'm sure if you have questions where they pop up, that Dietrich Burde can answer this much better than I can. I actually like to view these post-Lie algebra structures very often in a different way, slightly different way, which makes them maybe easier to me. And that's also the way in which I encounter them. So I look at these post-Lie algebra structures via representations. Oh, yeah. And so for this, I consider the Lie algebra and semidirect its derivation subalgebra. Yeah, so it's a semidirect product. And let us recall that the Lie bracket in this semidirect product, so I now use another type of bracket, let's say bolt square brackets. So this is the Lie bracket inside here. Yeah, so of such a semidirect product, this means you first take the bracket of the two elements in n. So this is the curly bracket. Then you apply this derivation to x2 minus the second derivation applied to x1. And then in the second component, you have the Lie bracket of the two derivations, which you just force the product, well, the composition minus the composition in the other direction. So this is the Lie bracket on the semidirect product. And now the lemma, or the way that I like to view very often post-Lie algebra structures, is if you have a pair of Lie algebras, yeah, based on a vector space V. So you have square brackets and curly brackets on this vector space B. Then a bilinear product, yeah, where the left multiplication map L is denoted by L, is a post-Lie algebra structure. If and only if you look at this map from G, well, up to here, let me comment a bit on this in a moment. Sending X to this tuple, this has to be a representation. Yeah. Of course, I am lying a little bit. We do not yet know that L ends up inside there n. So you should read this as, first of all, this is a PA if and only if L has its image in the derivations of n, and this map is a representation. Yeah, this is what I really want to say. Okay, so let me comment a little bit and say, give a sketch of a proof of this lemma. So assume that this is a bilinear product and is a PA, then of course I will end up in the derivations of n using L, and I can write up this map. And the other way around, if I can write up this map and this is a representation, then at least condition 3 will be satisfied because L of x is a derivation. So I only have to bother about condition 1 and 2. And now asking that this is a representation is saying that the image of the Lie bracket of xy, so this is the image of the Lie bracket of xy, should be the Lie bracket of the two images. Yeah. And so let me write out the Lie bracket of the two images. So by what is written above, I first have to take the bracket of x and y, then d1 applied to x2 minus the other one, and so on. Yeah. Okay, and now you just write what it means to be left multiplication, what it means to be left multiplication. And then if these have to equal to each other, then of course xy has to equal this part. Yeah, so we get this condition, which was really the first condition in the definition of a post-Lie algebra structure. And then the last one shows that left multiplication by xy should be these left multiplications. So if you apply this to a z, this is written up like this, and this is the second condition. So this is really the same thing as a post-Lie algebra structure. Yeah. So remember this for a moment. A PA's post-Lie algebra structure is actually the same as asking that this is the representation. Okay. So what have we been doing with these post-Lie algebra structures? Well, one of the main things that we have been doing together with Dietrich and many of our students is the following. So suppose we have a post-Lie algebra structure on a pair of Lie algebras Gn, and assume that we know something about the structure of G. For example, we know that G is abelian or nilpotent or whatever. Can we say something about the structure of N? Are there some restrictions on what N can be if we know something about G? Or vice versa, if we know something about N, are there some restrictions on the possibility of G? And even maybe there are rigidity results in the sense that if G satisfies some properties, then maybe if we have a post-Lie algebra structure on such a pair, then necessarily G has to be isomorphic, N has to be isomorphic to G, or vice versa. And actually, one of the first results we could prove is the following. So if G is simple, you take a simple Lie algebra, and you assume that there is a post-Lie algebra structure on a pair G and N, then necessarily N has to be isomorphic to G. Excuse me. And in fact, even the possibilities for the post-Lie algebra structure for the bilinear product are very restricted in this sense. And so we were actually wondering also, what happens if we move from simple to semi-simple? You see, this result we proved in 2012. And actually, we could only answer this question in 10 years later. Okay, what was the situation up till recently? And we often use this kind of tables to summarize our results. So let me explain a little bit how to read this table. So we look at structural properties of G and of N. And of course, when I write, for example, G is nilpotent, then I mean it's nilpotent and non-abelian. When I write solvable, I mean solvable but not nilpotent. Semi-simple means semi-simple but not simple. Reductive means not semi-simple. Complete can mean also solvable. So it's complete can be a solvable complete one. Of course, the same for N. Now, if we write a dash in our table, for example, here semi-simple and N nilpotent, this means that there is no post-Lie algebra structure in the situation where G is semi-simple and N is nilpotent. On the other hand, if we use a check mark, G solvable, N nilpotent, that does not mean that for any solvable Lie algebra G and a nilpotent Lie algebra N on the same vector space there exists such a structure. No, it just means that there are examples of solvable G and nilpotent N for which we have a post-Lie algebra structure on that pair. So there is at least one example. And as you see on the diagonal, we always have check marks because the zero product always gives a post-Lie algebra structure on a pair GG, for example. Okay, so up till recently in our table, we still had 6 question marks that we didn't know the situation. For example, is it possible that there is a post-Lie algebra structure on a pair Gn where G is semi-simple and N is reductive but not semi-simple? Okay, and so some other question marks. Well, we were able to answer some of these question marks. And so the first one is really about the semi-simple case. And this is really such a strong rigidity result, saying that if Gn is a pair that admits a post-Lie algebra structure where G is semi-simple, then automatically N has to be isomorphic to G. There is no other possibility. So certainly N cannot be reductive and not semi-simple. It has to be semi-simple and even isomorphic to G. And the proof is now quite easy. So remember, having a post-Lie algebra structure means that we have an embedding from G to N semi-directed derivations, sending x to x comma L of x, the left multiplications. And of course, what I will not use the full Lie algebra derivations of n, but I just look at the image L of G. Yeah, so you look at this subalgebra, and then the image of V is lying inside n semidirect L of G, the linear, the image of L. Now, it's not so difficult now to see that n semidirect L of G is the same as the image of G, direct sum L of G. Okay? Why? Well, you see the image phi of G is everything of the form x comma L of x. Yeah? And of course, then you can write any element of n as this element minus, let's say, the vector 0 comma L of x, which lies inside this thing. Yeah? So it's easy to see that as sums they are the same. And it's also easy to see that this is a direct sum. Yeah? Yeah, because if you have something in the intersection, then the x has to be 0, and then everything has to be 0. Okay, phi is a representation. Simple, and this guy is semi-simple, or 0, but then everything becomes trivial. So these two are semi-simple. So this means that this is a strongly Di-semisimple Lie algebra. So this Lie algebra is semi-simple by our main result from part 1. So we have shown that this is a semi-simple Lie algebra. And since n is an ideal of a semi-simple Lie algebra, n has to be semi-simple itself. Okay, that's already something. So we certainly know already that n has to be semi-simple. And moreover, by Kozlo's result, this n semidirect L of G has to be isomorphic to the direct sum of n and L of G. And it's the same Lie algebra as this one, which is isomorphic to the direct sum. Phi of G, well, x goes to x comma something. So phi of G is the same as G plus L of G. And now it's quite easy to see that if you have two semi-simple Lie algebras, such that this direct sum is the same as this direct sum, and these are the same ideals, then these two have to be the same. This all follows from the fact that the decomposition of a semi-simple Lie algebra into ideals is unique up to the order, up to isomorphism, of course. So conclusion, n has to be isomorphic to G, and this solves one of the question marks. So we see that this situation is not possible. The next thing we want to solve is actually the reductive case. And let's see how easily we can solve two of the three question marks in this setting. And this is actually something which is also a general and, let's say, easy thing to do. So if you have two vector spaces, a V1 and a V2, and you have a pair of Lie algebras G1 and N1 on a V1 and the G2 N2 on a V2, then of course you can consider the pair G1 plus G2 N1 plus N2 on the vector space V1 plus V2. And it's really trivial to see that if you have a post Lie algebra structure on this one and a post Lie algebra structure on the second one, then the combination of the two will be a post Lie algebra structure on the combination of the Lie algebras. Now, what can we do? Well, you see here that there are examples of G reductive and N abelian. So you can consider the situation where G1 is reductive and N1 is abelian. There are examples of this. And then secondly, there are also examples where G is abelian and N is nilpotent or solvable. So for the G2 and the N2 part, I will take G2 abelian and N2 either nilpotent or solvable. Okay, reductive plus abelian is of course reductive. So this guy is reductive. Abelian plus nilpotent is of course nilpotent, or abelian plus solvable is solvable and non-nilpotent. And so this means that we do have a post Lie algebra structure on such a pair, reductive and nilpotent or solvable, and so we can get two more check marks over here. So just some examples. This question mark, well, that's still a question mark. What did we do in the complete case? Well, actually, this was just doing some calculations, trying a little bit, and finding examples. Yeah. So for this one, G complete and N sample, we showed that we could actually find a structure on a pair of Lie algebras Gn, where in the first case N is SL3C, and for G we found a subalgebra, a Lie algebra, which is isomorphic to, let's say, the affine Lie algebra in dimension 2. So this is the SL2 semi-direct C2, the SL1 semi-direct C. So actually, this is a two-dimensional solvable one. Both are complete, so the direct sum is also complete. So we find an example in this situation. And for the semi-simple case, also we found an example. Yeah, you take SL2 plus SL2, which is semi-simple, and then we found some post-Lie algebra structure on a pair where G was just the sum of 3 times the two-dimensional solvable Lie algebra. So we could indeed also solve these 2 question marks by just giving examples. And then this guy is still open, and our conjecture is that actually this cannot happen. Yeah. So if G is reductive and N is semi-simple, but not well, without the center, yeah, then this situation cannot happen. If it's really, well, if G is reductive and not semi-simple, N is semi-simple, then this situation cannot happen. We have proven some special cases of this conjecture, but the full proof is, well, still beyond reach for, in my opinion, but maybe Dietrich or Mina have some other idea about this. Okay, and this is everything I wanted to say. So thank you very much for your attention.
Okay. Thanks to Professor Dekimpe for this interesting talk. Are there any questions, comments, remarks? Okay, please. Oh. Okay, I have a question. Are there any results about Di-semisimple Leibniz algebras?
I have no idea. Maybe Dietrich, you know something?
I'm sorry, I think this has not been yet considered. I didn't see anything so far. Maybe Friedrich can say a little bit on it if he knows about it.
No, I don't know anything about it. I'm sorry.
Okay, we know what to do.
Yeah, I mean, for Lie algebras, there's a little bit more. First, I want to thank Karel for, thank you that you presented our paper in such an excellent form. This was really great. So we are very grateful. And this question about Di-semisimple, there is a bit more you can say, even if it's not strongly semi-simple, that you can use these pre-homogeneous vector spaces. And I will talk about in my talk. I also say already thank you for inviting me for such a talk. And if you want to hear more about that, this will come again in my talk. But for Leibniz algebras, I think nobody has yet looked on it. I mean, the motivation to look at this actually also comes from geometry. We had many geometric situations where this decomposition into subalgebras only as vector spaces arises naturally somehow.
Yeah, this is also the reason that Onashik has been studying this kind of decompositions into, yeah.
Yes, and so I don't know where this could be used for Leibniz algebras, actually.
Yeah. Okay. If there are no questions or other comments, let's thank Professor Karel Dekimpe again. And okay, so we will resume on next Monday. Okay.
Okay, I will try to attend also in the future, but.
Okay, bye-bye to everybody.
Bye.
Thank you.
Bye-bye.